I need to remind you and me that this is a quantum chemistry course. So I thought I'd put the periodic table back up here and remind us about that. And I want to show this thing back down here that you should know a lot about that now. 1s is something to do with the spin thing. And we'll find out that this M down here, this M number, is part of what we're dealing with the spin. So anyway, we need to do some background on this. You know, quantum chemistry, you'd have to have some extra math classes and so on to understand it, because I think, as you saw when we were doing those probabilities and the brackets and all that kind of stuff, that looked like a math class. Well, I'm going to step back, just like I did when I described what a state is. We're going to step back and look at the math that goes behind this. Now, this is as much for me as it is for you. So whether you skip it or not is unimportant to me, but it answers some questions. It answers some questions where the complex nature of all this came up. I think you've already seen that when we did the y basis. We had to have that imaginary component to the description of what we were doing in the y-axis. So that kind of forces the complex thing. So what we're going to be discussing is a quantum mechanical complex Hilbert space. Now this Hilbert space can have two dimensions, which is the simplest one. That's why I started there with the spin. That's the simplest one. So, but when we get to position and energies and momentum, we'll have infinite dimensions. That's going to be so much fun. So before we get there, I better warn you about Hilbert space so that you can slowly work your way into it without getting scared and running away and telling your mom that I'm too mean to you. Now you look at what we have seen before, but I'm going to go backwards and prove everything works correctly so that we're not just making assumptions just because I threw them at you on those previous videos. This is what we've been using. Now, I kind of did some hand waving and said, oh, pi over 2 works for the, theta over 2 works for the probabilities. And so that's what we'll plug in there, and these two multiply together. It gives us 1. It helps us. No, let's not do that just yet. Let's go back a little bit and see what this state vector is. And you should know what a state is by now. That describes whatever physical system we happen to be working with, and that happens to be, guess what? What I'm most interested in is electrons in chemistry, because that tells us so much. Here's a Greek alpha and a Greek beta instead of this stuff. Well, what are we going back to that for? Because I want to show where this stuff comes from. And if you don't care where stuff comes from, then you probably haven't watched many of these videos anyway, because you don't want to dig into stuff and really understand it. Alpha and beta are elements of complex numbers. So what's a complex number? How do we define each of those complex numbers? And if both of these are complex, how come this one doesn't have any complex pieces of it and this one does? How can that be? Here's an imaginary component over here, but there's none here. How do we get away with that? If you don't remember what a complex number is, let's look at it this way. Alpha is a real number plus I. What's I? I is defined as something that when you square it, you get -1. Here's another real number. Here's a real number, and here's an I times a real number. Now, those are both complex values. So let's look up here at this. This should be a complex value. This should be a complex value. Well, it really is, because this is a complex value. It just happens to be that B is 0. If B is 0, then that one doesn't have any I stuff. This one does have some I stuff, so its complex number has some imaginary, has a non-zero coefficient here in the D. Now, another thing that I make mistakes on a lot, so it might happen to you, is when you see these two bars here, you're thinking, oh, that's absolute value. So that means that if it's if it's negative, then you just take the positive value of it. Well, that's a little simplistic, because in complex numbers, we take the complex conjugate. Now here's the complex conjugate. See, it was plus, now it's minus. And we multiply those two together and then take the square root of it. So there's no way that this is going to be a negative number, and there's no way that it's going to have any imaginary components to it. Because look at what happens. If you multiply these two together, you get the is it the sum of the squares? Let's see what happens. No, you get this difference of the squares. And what happens there? Okay, if you square -1 and +1, you're going to get a negative I squared, but I squared is -1. So you're really going to get the sum of the squares with this type of thing. So it'll be a squared plus b squared, take the square root of it. Oh, that sounds like a magnitude that you would put with vectors and so on. The a squared plus b squared, take the square root of it, that's the magnitude. That's what's going on here. It just happens to have complex numbers that you probably never worked with. Or if you have, maybe you didn't even know what you were doing, or you might be a heck of a lot smarter than me. Why is this up here? If we talk about vectors, your mind automatically says, okay, if this is a vector, then this must be two vectors added together to get the third vector. Yeah, that's pretty much the case. You weren't wrong in that. And we have basis vectors, and your comment, it might be, okay, what's the length of these? Well, the length of them, if we say that they're unit length, that's going to make life easy in your head, but they don't really have to be unit length. And I've got this saying that one of the basis vectors is plus z, and one of the basis vectors is minus z. And this assumes that we're measuring along the z-axis. As we set up a different basis when we have a different measurement method. So you set up any basis you want, and it'll still come up with can represent the same state. What's this 1 over 0, 0 over 1? Well, when you represent vectors, you can do it, if you're in linear algebra, as a column. And there's only 2 dimensions, so this column only has 2 dimensions. And I went ahead and used the unit length because that's easier to think about, even though it doesn't have to be that way. Now, if we were to represent this state vector, here's the way that what we're looking at. We're looking at, we could put on the plus z, we could take the cosine theta over 2 and project onto this unit vector, and it would fit, wouldn't it? Because that's going to be less than 1, and this one's going to be less than 1. So it could fit down here. And we could add those 2 vectors together. We'd get a little arrow up in this direction, and then we'd be all nice and we'd say, oh, we have completely defined the vector here. But what about this phase thing? All right, I challenge you, draw this picture with a phase. What are you going to do? You're going to have an arrow coming out of the page, into the page. How are you going to do that? The answer is you can't really draw it to any kind of usable method because the phase thing is going to show a relative difference between an arrow that you draw and another arrow that you draw. Or you could say, well, you could say a lot of things, but this shows that is not going to be easy to draw. And so all we can represent is the magnitude of those two. Now, the relative magnitude is what determines the state. Just the relative magnitudes determine the state. So that means, well, I guess I will allow myself to draw a little bit more. Here's the alpha, and I've got the magnitude signs around it. And here's the beta with the magnitude signs around it. And here I go out this way. Here's the dimension of this arrow. And this arrow represents one quantity of the state. It represents the relative phase, wrong, represents the relative magnitudes between these things. And the relative phase, which is what this represents, that doesn't show up on this page. All it is the relative magnitudes. Now, how long is this arrow? You might say, well, it's right there in front of you. Who would say it's anything else? Well, actually, that arrow could be this long. The arrow could go out in this fashion. As long as the relative magnitudes are the same, then it represents the same. And here's a new term. Let's see if I can put that on here. This defines the ray. So there's a whole class of vectors that fit into this. I've got this broken out here for the phase to kind of show that maximum phase shift will be all I, or it could be negative I, depending on the phi here. In other words, this could be a 1 or a negative 1. So it could be all plus I or all minus I, and the cosine would be, this value would just be 0. So I think you kind of get the idea how that phase works in and out on this value, but it really controls how much of the I value you have. If the I value is not existent at all, then this sign of phi is what it would be, either 0 or pi. One thing that I need to cover is, why did I choose theta over 2? It would appear that the theta angle relates to the z basis that we're talking about. In other words, if theta were 0, then you'd get plus z all the time. So I'm going to refer you to the next video in this series. I recorded it earlier, but I'm going to plug it into the playlist here immediately after this video, and that will explain where this theta over 2 business comes from.